Welcome to this explainer. Inside a nuclear reactor core, you've got this chaotic, high-pressure mix of steam and water. Today, we're going to dig into the incredible science that lets us predict and control that chaos, because when you're talking about nuclear power, safety is, well, everything. So to make sure everything is absolutely safe, engineers have to predict exactly how this turbulent, high-energy mixture behaves. The question is, how on earth do you model something that complex? All right, here's how we're going to tackle this. We'll start with a basic principle of physics and then build our way up to the really sophisticated models engineers use today. Okay, let's dive in.
Okay, so before we can even think about two fluids interacting, we've got to get a handle on the forces at play in just one of them.
You know, in simple terms, momentum is just the push that a fluid has. If you want to change its direction or speed, you have to apply a force. And this principle, it lets us calculate exactly how much force we need. Just think about water flowing through a bend in a pipe, right? Using that momentum principle, we can figure out the exact force the water puts on that bend. And for an engineer building that pipe, that's absolutely critical information.
So that's all well and good for one fluid. But inside a reactor, you've got two phases, liquid and gas, all mixed together. And that's when things get, well, chaotic, fast.
And see, this mixture isn't neat and tidy. It doesn't just stay uniform. Instead, it can form all these wild, unpredictable patterns. Scientists have a name for them: flow regimes. So the big question is, how can you possibly create a single model that works for all this chaos? I mean, you can't just treat it like an average fluid. The physics for bubbly flow is totally different from droplet flow. So yeah, scientists needed a much, much cleverer approach.
And that brings us to the solution. This was developed by scientists at places like Argonne National Laboratory, and it's called the two-fluid model. And the core idea here is just, it's brilliant. They said, okay, let's stop trying to model the messy mixture. Instead, they decided to model the liquid and the gas as two separate fluids. They each get their own set of equations, but they occupy the same space and, crucially, they interact with each other.
Think of it this way. It's like trying to predict the movement of two big crowds running through each other in a hallway. You can't just model the average person, right? No way. You have to model each crowd separately. And, this is the key, you have to model how they bump into each other. And that interaction, that bumping into each other between the two fluids, that's the most important part. It's also the hardest part to get right. So let's take a look at the key forces involved. Now, what's really cool about this diagram is how it breaks down all the forces. You've got pressure, you've got gravity, wall friction. We can account for all that. But the secret sauce, the real magic, is right here in the middle. The forces acting at the interface between the water and the steam. So what is that? It's something called interfacial drag. It's basically the friction-like force that slows down a bubble as it rises through water. And getting that drag calculation right, that is the absolute key to making the whole two-fluid model work. But here's the catch. This drag isn't just one simple number you can plug in. As you can see from these graphs, that drag changes a lot. It depends completely on which of those flow regimes we saw earlier is happening. The model has to be smart enough to account for all of that. Okay, so after all that complexity, modeling two separate fluids, figuring out their ever-changing drag forces, you have to ask, does this complex math actually work in the real world? And the answer is a resounding yes. This is the payoff right here. The solid line is the model's prediction, and the little circles, that's real-world experimental data. They match up almost perfectly. And it's not a fluke. We see it again and again. Even with totally different materials, the theory lines up beautifully with the data. What this tells us is that these models, when you build them right, are incredibly powerful at predicting what's actually going to happen. So let's put it all together. What's the process? First, you define the physical system, the exact shape of the reactor channel. Then you apply those fundamental conservation equations, but you do it separately for the liquid and the gas. Step 3, and this is the crucial part, you use what are called closure relations to define how they interact. That's our interfacial drag. And finally, you feed that whole massive system of equations to a computer, and it solves it for you. And what pops out at the end? This. This is the final product, a clear set of predictions for what's happening at every single point inside that channel. It's what allows engineers to check and double-check those all-important safety margins. So it's really this incredible journey, right? We went from a simple, fundamental concept of momentum all the way to a super complex simulation. And it's all driven by the need for safety and a really deep understanding of the physics.
And of course, these models are always evolving, always getting better at handling even more complex physics, which kind of leaves you wondering, what other chaotic behaviors will we need to predict next? Thanks for joining us for this explainer.